Welcome! In this session, we'll explore LeetCode problem number 1447, Simplified Fractions. This problem challenges us to generate all simplified fractions between 0 and 1 with denominators below a given limit. Let's dive in and break it down step by step. In this problem, we are tasked with finding all simplified fractions between 0 and 1, exclusive, where the denominator is less than or equal to a given integer n. A fraction is simplified if the greatest common divisor, or GCD, between the numerator and denominator is 1. For example, fractions like 1/2 or 2/3 are simplified, while 2/4 is not because 2 is a common divisor of both the numerator and the denominator. The input to the problem is a single integer n, which will range between 1 and 100, and the output is a list of strings, each representing one of these simplified fractions. The fractions can be returned in any order, as long as they meet the criteria of being simplified and within the specified range. Let's look at the first example. If n is equal to 2, we need to consider all fractions with denominators of 2 or less. These fractions include 1/2. This is already simplified because the only common divisor between the numerator, 1, and the denominator, 2, is 1. Since there are no other valid fractions in this case, the output is simply 1/2. Now, for n equal to 3, we consider fractions with denominators of 3 or less. These fractions include 1/2, 1/3, and 2/3. Each of these is already simplified because their numerators and denominators do not share any common divisors other than 1. For instance, 1/3 is simplified because 1 and 3 share no common divisors other than 1, and the same goes for 2/3. Therefore, the output is 1/2, 1/3, 2/3. When n is 4, we evaluate all fractions with denominators up to 4. These fractions include 1/2, 1/3, 1/4, 2/3, 2/4, and 3/4. Among these, 1/2, 1/3, 1/4, 2/3, and 3/4 are simplified. For example, 1/4 is simplified because 1 and 4 share no common divisors other than 1. However, 2/4 is not simplified because both the numerator and denominator are divisible by 2. As a result, the output is 1/2, 1/3, 1/4, 2/3, 3/4. To ensure the solution handles all scenarios, there are some edge cases to consider. For n equal to 1, there are no valid fractions because the only potential fraction, 1/1, is not between 0 and 1. The output in this case is an empty list. On the other hand, when n is 100, the number of possible numerator-denominator pairs becomes very large, so the algorithm must handle these calculations efficiently. Additionally, fractions like 2/4 or 6/9, which are not simplified, must be excluded by checking the greatest common divisor between the numerator and denominator. Since the number of pairs to evaluate grows quadratically with n, the algorithm should efficiently calculate the GCD to avoid unnecessary overhead and ensure the solution runs within a reasonable time frame. To tackle problem number 1447, simplified fractions, our goal is to generate all fractions between 0 and 1, where the denominator is less than or equal to the input value, n. The challenge lies in ensuring that these fractions are in their simplest form. This means the greatest common divisor, or GCD, of the numerator and denominator must be exactly 1. One approach is a brute force method. The intuition here is to systematically generate all possible fractions by iterating through denominators from 2 to n and numerators from 1 to 1 less than the denominator. For each fraction, we check if the GCD of the numerator and denominator equals 1. If so, it's simplified, and we add it to our result set. While this approach is straightforward and easy to implement, it involves nested loops and frequent GCD checks, which can make it inefficient for larger values of n. The time complexity is n squared * log d due to the GCD calculation, and the space complexity is k, where k is the number of valid simplified fractions. Despite its simplicity, this method can be slow when n is large. Now, to make the brute force approach more efficient, we can optimize the GCD computation by using the Euclidean algorithm, which is a faster method for finding the greatest common divisor. The steps remain the same: iterate through all possible denominators and numerators, check if the GCD equals 1, and add the simplified fraction to the result. The key improvement here is the reduction in the time taken for each GCD calculation, which makes the approach marginally faster. However, the overall time complexity remains n squared asterisk log d, as we can't avoid the nested loops to examine all numerator-denominator pairs. Similarly, the space complexity stays O, k, for storing the results. While this optimization improves performance slightly, it doesn't change the asymptotic complexity. Another approach we considered was pre-computing GCDs for all pairs of integers. This would allow us to skip redundant calculations. However, pre-computing GCDs requires a substantial amount of memory, specifically O, n squared, which makes it infeasible for large values of n. Additionally, the time complexity for pre-computing all GCDs is O, n cubed, which is significantly worse than the brute force approach. Given these considerations, we chose the brute force approach with optimized GCD computation as the most practical solution. The key insight is that a fraction is simplified if and only if the GCD of the numerator and denominator is 1. By using the Euclidean algorithm, we ensure that these checks are performed efficiently. Although pre-computing GCDs can avoid redundant calculations, it demands too much memory to be feasible, especially for larger values of n. What solidified our choice was the realization that the problem inherently requires generating all valid fractions, so an O, n squared, solution is unavoidable. The only meaningful optimization is in the GCD calculation itself. This strategy balances efficiency and simplicity, making it the best fit for the problem constraints. Finally, let's consider the trade-offs and comparisons. The optimized brute force approach strikes a balance between readability, efficiency, and practicality. While theoretically slower than using pre-computed GCDs, it is far more memory efficient and performs well within the given problem constraints. Additionally, the brute force approach is straightforward to implement and scales reasonably well for typical input sizes. In conclusion, the optimized GCD-based brute force method is the ideal choice for solving the simplified fractions problem. It effectively combines simplicity, efficiency, and scalability, ensuring that the solution is both practical and easy to understand. To generate all simplified fractions between 0 and 1 where the denominator is less than or equal to n, we start by breaking the problem into clear steps. First, we need to ensure that the fractions satisfy specific criteria. The numerator must be greater than 0 but less than the denominator itself must not exceed n, and most importantly, the fraction must be in its simplest form. This means the greatest common divisor, or GCD, of the numerator and denominator must be 1. Next, we iterate over all possible denominators starting from 2 up to n, since a denominator of 1 cannot create any valid fractions in the given range. For every denominator, we then iterate through all possible numerators from 1 to 1 less than the denominator. This ensures that the numerators are always smaller than the denominators, keeping the fraction less than 1. Finally, we check each candidate fraction to determine if it meets the simplest form criteria using the GCD function. If the GCD is 1, the fraction is valid, otherwise, it is skipped. Fractions that pass the GCD check are then added to a result list in the format numerator/denominator. We repeat this process for all valid numerators and denominators until every possibility has been tested. After all iterations are complete, the result list containing the simplified fractions is returned. The key insight here is that using the GCD function is essential for ensuring that the fractions are in their simplest form. A GCD of 1 guarantees that no common factors exist between the numerator and denominator. Efficiency is also a consideration. While the nested loops have a worst-case time complexity of O, n squared, due to iterating over all numerators and denominators, the GCD computation is quite efficient, running in O, log, min, numerator, denominator, time thanks to the Euclidean algorithm. Combining these, the overall complexity of the algorithm becomes O, n squared asterisk log n, which works well within the given constraints. Additionally, by skipping fractions where the GCD is greater than 1, we avoid redundant calculations for fractions that can be simplified. This approach also leverages simple but effective data structures. The result list is central to storing the valid fractions, and each fraction is saved as a string in the format numerator/denominator for easy readability and output. The two primary operations involved are nested iteration over numerators and denominators, which ensures that all possible fractions are considered, and the computation of the GCD to verify whether a fraction is in its simplest form. Both operations are optimized for efficiency. For instance, the Euclidean algorithm used to compute the GCD is highly efficient, making it suitable for the problem's constraints. Moreover, by directly skipping fractions where the GCD is greater than 1, the algorithm avoids unnecessary checks and computations, further streamlining the process. Once the valid fractions are identified, they are formatted as strings and stored in the result list. This ensures that the output is both easy to read and simple to handle programmatically. The entire process can be summarized in a concise pseudocode implementation. First, we initialize an empty result list. Then, we iterate over denominators from 2 to n. For each denominator, we iterate over numerators from 1 to 1 less than the denominator. If the GCD of the numerator and denominator is 1, we append the fraction as a formatted string to the result list. Finally, the result list is returned. When considering edge cases, there are a few important scenarios to keep in mind. For example, when n equals 1, no fractions exist because no valid denominator can be greater than 1. For prime denominators, all numerators from 1 to 1 less than the denominator will result in simplified fractions since the GCD of a number with a prime is always 1 unless the number is a multiple of the prime. Handling larger values of n is made feasible by the algorithm's efficiency, particularly due to the use of the Euclidean algorithm for GCD computation. As an example, when n is 4, the algorithm proceeds as follows: start with a denominator of 2 and check numerators. 1/2 is valid since the GCD of 1 and 2 is 1. Next, for a denominator of 3, the numerators 1 and 2 both result in simplified fractions, 1/3 and 2/3, since their GCDs with 3 are 1. For a denominator of 4, check numerators 1, 2, and 3. 1/4 and 3/4 are valid as their GCDs with 4 are 1, but 2/4 is skipped because its GCD is 2, indicating it can be simplified. The final result for n equals 4 is 1/2, 1/3, 2/3, 1/4, 3/4. This approach systematically covers all possibilities, ensuring that the output is correct and efficient. The provided Python solution generates all simplified fractions between 0 and 1 for a given maximum denominator n. Here's the step-by-step explanation. 1. We begin by importing the GCD function from Python's math module. The GCD function is used to calculate the greatest common divisor of two numbers, which is essential for determining if a fraction is in its simplest form. 2. The simplified fractions function is defined with a single parameter, n, representing the maximum allowed value for the denominator. 3. An empty list, result, is initialized to store the simplified fractions as strings in the form numerator/denominator. 4. A nested loop structure is used to iterate over all possible denominators and numerators. The outer loop iterates over the range of possible denominators, starting from 2 up to and including n. A denominator of 1 is excluded because fractions with a denominator of 1 are not in the required range, 0, 1. The inner loop iterates over the range of possible numerators, starting from 1 and going up to 1 less than the current denominator. This ensures that the fraction is always less than 1. 5. Inside the inner loop, the GCD function is used to check if the greatest common divisor of the numerator and denominator is 1. If so, the fraction is in its simplest form and is added to the result list as a string in the format numerator/denominator. 6. After all iterations are complete, the result list containing all simplified fractions is returned. This approach efficiently generates all simplified fractions by leveraging the mathematical property of the greatest common divisor, ensuring that only irreducible fractions are included. The algorithm has a time complexity of approximately (n² log n, where the log n factor comes from the GCD computation for each fraction. This implementation is optimal for the constraints of the problem and adheres to the requirements of generating fractions in their simplest form. Here, we start with the implementation of the simplified fractions method. The goal of this method is to generate all simplified fractions less than 1 for a given integer n. To do this, we first create a list called result to store the fractions. Next, we use a nested loop structure. The outer loop iterates over possible denominators, starting from 2 up to the value of n, since a valid fraction must have a denominator greater than 1. Inside this loop, the inner loop considers numerators that are smaller than the current denominator, ensuring that the resulting fraction is less than 1. For every numerator and denominator pair, we check if their greatest common divisor, or GCD, is 1, which confirms that the fraction is in its simplest form. If so, we format the fraction as a string and add it to our result list. To calculate the GCD, we use a helper method, which we define below. The helper method GCD takes two integers, a and b, as input and computes their greatest common divisor using the Euclidean algorithm. The process involves repeatedly assigning b to a and the remainder of a divided by b to b, until b becomes 0. At this point, the value of a is the GCD, which we return. This method ensures that we can efficiently determine whether a fraction is in its simplest form, which is crucial for solving this problem. Once all valid fractions are added to the result list, the simplified fractions method returns the list containing the simplified fraction strings. To begin solving the problem, we start with the simplest case where the input is n equals 2. The first step is to initialize an empty list called result that will hold all the simplified fractions. Then, we enter the outer loop, which begins with the denominator set to 2 because a fraction's denominator must be at least 2. Inside this outer loop, we have an inner loop that iterates over possible numerator values that are less than the current denominator. For this example, the inner loop starts with numerator equals 1. At this point, we calculate the greatest common divisor, or GCD, of 1 and 2, which turns out to be 1. Since the GCD is 1, the fraction 1/2 is already in its simplest form. We then append this fraction as the string 1/2 to the result list. After this, both the outer and inner loops end because there are no more valid denominators or numerators to process. Finally, we return the result list, which contains the single fraction, 1/2, as the output for this input value of n equals 2. Now let's consider the case when the input is n equals 3. As before, we initialize an empty list, result, to store the simplified fractions. The outer loop begins with denominator equals 2, and within this, the inner loop sets numerator equals 1. We calculate the GCD of 1 and 2, which is 1, so the fraction 1/2 is added to the result list. Now, result contains 1/2. Moving to the next step, the outer loop increments the denominator to 3. For this denominator, the inner loop starts again with numerator equals 1. The GCD of 1 and 3 is 1, so 1/3 is added to the list, making result equals 1/2, 1/3. The inner loop then continues with numerator equals 2. The GCD of 2 and 3 is also 1, so 2/3 is added to the list, resulting in result equals 1/2, 1/3, 2/3. At this point, there are no more valid numerators or denominators to process, so the loops end. The final result for this input is 1/2, 1/3, 2/3, which is returned. For the case where the input is n equals 4, we again start by initializing the result list as empty. The outer loop begins with denominator equals 2. The inner loop sets numerator equals 1, and the GCD of 1 and 2 is calculated as 1. Since the GCD is 1, the fraction 1/2 is added to the list, making result equals 1/2. Next, the outer loop progresses to denominator equals 3. For this denominator, the inner loop starts with numerator equals 1 and calculates the GCD of 1 and 3, which is 1. Therefore, 1/3 is added to the list, resulting in result equals 1/2, 1/3. The inner loop continues with numerator equals 2, and the GCD of 2 and 3 is also 1, so 2/3 is added, giving result equals 1/2, 1/3, 2/3. Now, the outer loop moves to denominator equals 4. For this denominator, the inner loop begins with numerator equals 1, and the GCD of 1 and 4 is 1, so 1/4 is added, making result equals 1/2, 1/3, 2/3, 1/4. The inner loop proceeds to numerator equals 2, but the GCD of 2 and 4 is 2, so this fraction is skipped. Finally, for numerator equals 3, the GCD of 3 and 4 is 1, so 3/4 is added to the list. The final result after all iterations is 1/2, 1/3, 2/3, 1/4, 3/4. The final output for the input n equals 4 is 1/2, 1/3, 2/3, 1/4, 3/4. This output represents all the simplified fractions where the denominator is less than or equal to 4 and the numerator is less than the denominator, ensuring that the fractions are in their simplest form. The solution works by systematically iterating through all possible numerator and denominator pairs, checking their greatest common divisor, and including only those pairs where the GCD is 1. This ensures that every fraction in the output is irreducible and meets the problem's requirements. To analyze the time complexity of this algorithm, we start by examining the operations it performs. The outer loop is responsible for iterating through all possible denominators from 2 to n. This gives us a total of n1 iterations for the outer loop. Within the inner loop, for each denominator, we iterate over all possible numerators from 1 to 1 less than the denominator. For a specific denominator d, the inner loop runs d 1 times. If we sum these iterations across all denominators, we get 1 plus 2 plus 3, and so on, up to n1. This summation can be expressed as en1 asterisk n divided by 2, which simplifies to O n squared. This is the total number of iterations of the nested loops and forms the base of our time complexity analysis. Now, let's consider the time complexity of the GCD calculation, which is performed during each iteration of the inner loop. The GCD function has a complexity of O log min a b, whereas the numerator in b is the denominator. In the worst-case scenario, this becomes O log d for a given denominator d. Combining this with the total number of iterations derived earlier, the overall time complexity becomes a summation of terms involving the inner loop iterations multiplied by the logarithmic factor. Specifically, this is expressed as the sum of d1 multiplied by O log d for all denominators from 2 to n. In the worst case, this simplifies to O n squared asterisk log n, as the logarithmic factor increases with the denominator. Thus, the overall time complexity of the algorithm is O n squared asterisk log n. Turning now to the space complexity, the primary contributor is the result list, which stores all the simplified fractions. The number of simplified fractions for a given n is less than the total number of numerator-denominator pairs, which is n1 asterisk n divided by 2, or O n squared. Each fraction is stored as a string, and while the exact size of each string depends on the number of digits in the numerator and denominator, this size is considered O1 for simplicity. Therefore, the space complexity of the result list is O n squared. Additionally, the GCD function uses space on the call stack due to recursion. The space required for the GCD function is O log d, where d is the denominator. However, this contribution is negligible compared to the result list. As a result, the overall space complexity of the algorithm is dominated by the result list and is O n squared. When comparing this approach to a brute force solution, we see that the brute force method would generate all possible fractions for denominators from 2 to n and numerators from 1 to 1 less than the denominator. Each fraction would then be simplified by dividing by their greatest common divisor, or GCD. This approach would still result in an O n squared asterisk log n time complexity due to the GCD calculation. The optimized approach used here avoids generating invalid fractions by directly checking for coprimality within the loops, making it more efficient in practice. In terms of best, average, and worst-case analysis, the time complexity remains O n squared asterisk log n in all cases. This is because the algorithm must evaluate every numerator-denominator pair and compute the GCD for each, regardless of the input structure. Finally, we can validate the big O complexity of this algorithm mathematically. First, the total number of iterations is the sum of d1 for all denominators from 2 to n. This sum simplifies to n1 asterisk n divided by 2, which is O n squared. Next, each iteration involves a GCD calculation with a complexity of O log d, which is bounded by O log n. For the largest d, combining these results gives us an overall time complexity of O n squared asterisk log n. For space complexity, the result list is the dominant factor, growing as O n squared, while the GCD function's recursive call stack uses negligible space in comparison. Therefore, the space complexity of the algorithm is O n squared. A common source of mistakes in solving this problem is failing to check if a fraction is in its simplest form. For instance, if you generate 2/4, it should be reduced to 1/2 by using the greatest common divisor, or GCD. Without this step, your solution might produce duplicates or incorrect results. Another issue is including improper fractions or those equal to 1. The problem specifies that only fractions between 0 and 1 are valid, so entries like 4/4 or 5/3 must be excluded. To ensure this, always validate that the numerator is smaller than the denominator. Iteration bounds can also introduce errors. For example, some solutions mistakenly allow the numerator to go up to the denominator, leading to invalid fractions. Lastly, inefficient GCD calculations can significantly slow down your solution. Instead of recalculating the GCD repeatedly, consider using optimized algorithms like the Euclidean method or memoization to improve performance. Skipping edge cases is another common pitfall. For example, when n equals 1, there are no valid fractions, but some solutions fail to account for this. Additionally, when n is very large, performance issues can arise if your solution isn't optimized. From an interview perspective, solving this problem effectively demonstrates your understanding of number theory and algorithmic efficiency. Knowing how to use the GCD function to simplify fractions and avoid redundant computations is crucial. Leveraging GCD not only ensures correctness by eliminating unnecessary results early but also improves computational efficiency, reducing both the output size and runtime. Be ready to discuss edge cases such as n equals 1 or n equals 1000, and explain how your solution scales with input size. Highlighting trade-offs is also important. While a straightforward n cubed solution may be easier to write initially, it's impractical for larger inputs. Instead, aim for an optimized approach with n squared asterisk log en complexity, which uses the Euclidean algorithm for GCD calculations. This problem connects well with several related problems. For example, in LeetCode 970, powerful integers, you also generate valid outputs within specific constraints. Similarly, LeetCode 1018, binary prefix divisible by 5, involves modular arithmetic and careful iteration, which could help you think about edge cases and efficiency. LeetCode 202, happy number, focuses on using mathematical properties to generate and validate sequences, which aligns with the theme of this problem. Finally, LeetCode 412, FizzBuzz, simplifies mathematical patterns but centers on divisibility, offering a more basic but related challenge. Exploring these problems can deepen your understanding of mathematical reasoning and efficient computation, both of which are critical for solving the simplified fractions problem effectively. There are several approaches you can take to solve this problem. A brute force method involves iterating through all possible numerators and denominators and checking if each fraction is simplified. While this is easy to implement, the n cubed time complexity makes it inefficient for larger inputs. A better approach uses the GCD function to filter fractions. By nesting loops for the denominator and numerator and verifying that GCD, numerator, denominator, equals 1, you can reduce the complexity to n squared asterisk log n. This method is both efficient and accurate but requires an understanding of GCD optimization techniques. For even greater efficiency, you could pre-compute GCDs for all possible pairs using dynamic programming. This eliminates redundant calculations during iteration, trading higher memory usage for faster runtime. Each of these methods has its trade-offs, so the best choice depends on the input size and the constraints of the problem. Great job making it to the end. To recap, we used the greatest common divisor to efficiently generate simplified fractions. This problem highlights the importance of mathematical reasoning in coding. Keep practicing, and don't forget to check out other challenges. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!